This short video will demonstrate the technique of factorisation by the perfect square, or sometimes referred to completing the square. So this is the quadratic that we have to solve, and just a reminder, I've drawn a diagram here and shown the perfect square rule. So remember, a perfect square is when we have x plus a constant squared, which expands to be x squared plus 2 times the constant times x plus k squared. So I can represent that on the diagram here. The x squared term is this large section of the diagram. 2 times k times x, well, each of these parts would be k times x. That distance would be k, that would be k, and the last little bit, the missing bit, is the k squared. So let's see how we can use that rule in our formula. The first thing I note is that the coefficient in the rule of the x squared term is 1, but I don't have that, I have 2. So I'll divide everything by 2. So divide by 2, divide by 2, divide by 2, 0, divide by 2. Now the x squared term has a coefficient 1, just like the rule. The next thing to look at is the second part, 2 times k times x. In our equation we have negative 15 as the coefficient of x. So 2 times k is the same as negative 15. K must be negative 7.5, or better to express it as negative 15 over 2. Negative 15 over 2. So this would be negative 15 over 2 by x as the area of this, and negative 15 over 2 by x for the area of this rectangle. And by the time you add both of them, it's negative 15x. The problem is, of course, the missing bit down here. The missing bit down here would be negative 15 over 2 for that length by negative 15 over 2 for that length. In other words, it's negative 15 over 2 squared. But that's not what we've got. We've got 40. If we want to complete the square, I will need to have a negative 15 over 2 squared added on at the end of this expression. And I know you're going to say, wait a minute, you can't just change things. Well, it's all right, I'll take care of that. I will also add the negative 15 over 2 squared to the other side of the equation to keep it balanced, and I'll transpose the 40 to become negative 40 so that it isn't forgotten about, but it's not in the way of my lovely perfect square quadratic. This now is in exactly the format we need for the perfect square quadratic. So I'll factorise. X is the first term. The constant k is the negative 15 over 2. So I add on negative 15 over 2 squared. From this step to this step is literally going this rule from the right hand side to the left hand side. We're running the rule in reverse. We can only do that because we carefully chose the appropriate value to write here at the end of the quadratic, the missing part, to complete the large square. That's why it's called complete the square. Now we have a little bit of work to do here. Negative 15 by negative 15 is 225. 2 squared is 4. Minus, and 40, well, I'd rather express this as something over 4. That will be 160 over 4. X plus negative 15 over 2 squared equals, now I'll express this all over 4. 225 minus 160 is 65 over 4. Time to take the square root of both sides now. X plus negative 15 over 2 equals plus or minus the square root of 65 over 4. Transpose this becomes positive 15 over 2, plus or minus, and this is better as root 65 over 2. Root 65 is not a perfect square and it can't be simplified. If it could be simplified, still using surds, I would have done so. And finally then we would say negative 15, or what did I say, positive 15, plus or minus root 65 all divided by 2. There's the solution to our quadratic. If we had to express this approximately, usually we'd say to say 3 decimals. Let's see if you can see the calculator screen there. So I'd use the, that's not going to work, is it? What if you can still see the keyboard there? Just having trouble getting everything on the keyboard. So I'll use the fraction key. I'll enter 15 plus the square root of 65 over 2. It gives me the answer exactly in surd form. I press the key here, standard to decimal form, and it's 11.53. If I just go back and edit the calculation to be subtract, once again standard decimal, 3.47 or 3.47. There's my 2 solutions. There's another way we could have solved this too. We could have used the calculator. Oh, there's a bit of a reflection going on there on the screen of the calculator, isn't there? There you are. So we could go back to the menu, to the graphing app. Now you'll note my original equation here. I've already entered it here in the first function, and I'll draw that. Now if you need to, you can change the window settings or the zoom, but you can see I have a parabola here. I'm interested in when this equation had a value 0. Now that would correspond to a y coordinate 0. We want to know the value of x. In other words, we want to know the value of x at this point and this point here. I can find that quickly with F5, which is gsolve, and then the roots of the equation refer to these 2 points. So I press that, calculator found for me that the first root was at x equals 3.46, just like we calculated here. Use the right arrow and I get the second root, 11.53, just like we found there. So that's a quick demonstration of factorising quadratics using the completing the square technique. Once you get the hang of it, you don't need to draw these diagrams, just have to do the algebra and you're all good.